Actually, Focon is an excellent example for the things we do and want to do in the future. Because, in Focon, we actually do two things. One is we work on quantum mechanical calculation for the materials and for the devices themselves using conventional computers. And, on using quantum computers in the future to also do this type of material calculation, the material science calculations, and also device calculations if necessary. I don't know. I mean, of course, we are, I think, still a little bit away from using a quantum computer to simulate a quantum computer, but sooner or later it's going to happen.
Hi, everyone, and welcome to this episode of the podcast. Today, we have Michael Marthaler, who holds a PhD in physics from Karlsruhe Institute of Technology, or KIT. He has a research background in quantum computing and is currently the CEO and co-founder of HQS. HQS is a company that provides software for quantum modeling of molecules and materials. So, Michael, without further ado, thanks a lot for joining today.
Yeah, thanks for having me, Niklas.
I figure that we could start the discussion by talking about your research background briefly. So I
Yeah,
know you have
sure.
a research background in quantum computing, I think specifically superconducting qubits. What would be very interesting for me is if you could talk briefly about how the space has evolved during the course of your career. So when you first got into it, what the industry looked like compared to today.
Yeah, that's actually a really interesting trajectory. When I first heard about quantum computing, it was in 2003 when I was still a student. And I think this was like a first high point of quantum computing. So kind of the basics, the theoretical basics had been laid out in the 90s. And then like the first successful experiments and kind of the first qubits had been built like in the late 90s and beginning of the 2000s. And then 2003 was, I think, a pretty high point. And then I started to work in it like with my master thesis and then later PhD thesis in 2005-6. And I think this was basically also the first actually downward trajectory, like the first hype cycle had been through, so to say. Yeah. So yeah, 2002-3, the top of the hype cycle, 6-7. I don't know, a little bit more, let's say, pessimism. Not necessarily pessimism, but let's say kind of uh, a need to improve things, but also, as everybody has seen this idea of the hype cycle. Probably many people know it. I have a topic that comes, then like there is generally a tendency to have too much expectations. Then basically the hype cycle kind of achieves its peaks, and then people are a bit dissatisfied. But then as you go down from the hype cycle, kind of from the hype peak, you kind of come to what's often called the plateau of productivity, which means you start to again work, let's say, step by step through problems. And I think in 2006-7, this actually happened. Uh, and a couple of key improvements were made, especially in superconducting qubits. So just very briefly, superconducting qubits means you have a metal structure on a semiconductor surface and you go to very low temperatures, like 20 millikelvin, so that's barely above zero, but doable in a nut. I mean, it's relatively standard. It's expensive to do it, but it's relatively standard. And uh, in 2006-7, basic superconducting qubit structure was proposed, how to build it, that I think currently is the standard, and that showed rapid improvement in the quality of the quantum mechanical bits. And maybe let's expand a little bit on this quality issue. And the major problem with building a quantum computer is that the basic unit of the quantum computer, the qubit instead of bit, quantum mechanical bit. So the qubit is intrinsically sensitive to errors. And maybe I can also even shortly explain this. I mean, why is the digital electronics so awesome? The classical digital electronics with bits is so awesome because, if you want to have a bit, you need a signal that is like 0 or 1. And if your signal is slightly wrong, I don't know, it's still roughly, can say current is on and current is off. And even if it's not completely off or not completely on, it doesn't matter. You can still clearly distinguish 0 or 1. It's awesome. In qubits, that's different. You have to have something more continuous to distinguish, and then errors very naturally creep into your calculation, and that makes qubits intrinsically sensitive to perturbation and noise. And this was the critical part that needed to improve in the 2010s. And yeah, I mean, basically, key kind of architectural ideas were proposed. And my personal major topic I worked on as a theoretical physicist was the basic mechanisms of how these perturbations come about, what the material issues are that you need to improve, how you could kind of reduce certain coupling of these qubits to external source of perturbation and so on. And the whole topic is called decoherence theory. So that was my topic in the area of superconducting qubits. Mm-hmm. So rapid improvements were made, and then a couple of additional really big breakthroughs were made in the 2011 and 12. Still all academic, but I think in the 11, 12, a couple of really good improvements were made in the quality of qubits that were really massive jumps. And as a key point, of course, if you look at academic work, one group showed that you can do it, and a huge amount of other academic groups immediately repeated it. That shows you that this is really sustainable academic progress, and not just like a single nice work, but that cannot really be reproduced. Yeah, that often happens in academic work. But so this was clearly a breakthrough that was fundamental and reproducible in many cases.
Is it possible to summarize what that was? Or is it too technical?
Well, I mean, I can actually summarize it. So as I said, the superconducting qubits are metallic structures on the surface of a semiconductor or of an insulator. And in some sense, the major problem is that you have the semiconductor, the metallic superconductor, and on top of it, an oxide, which just naturally happens. Yeah, you have some metallic material, aluminium, for example, which is superconducting at low temperatures, and of course, on top you have an oxide. And then you have a distribution of electromagnetic fields in this metallic superconductor, or in the superconductor. And you want to have this electric field should really be not very strongly focused in the oxide, because the oxide absorbs energy, and that absorbs, then creates errors in your state of your quantum mechanical bit. And it turned just out that if you make your superconductor larger, meaning you make your overall bits larger, which is a bit counterintuitive. Yeah, I mean, we always think about miniaturization being like more quantum mechanical or so. Yeah, things getting smaller, there's more quantum mechanics. So intrinsically, you would think you have to make things smaller, but it turned out you make it bigger. And then the electromagnetic fields distribute in a way that it's less inside of the oxide. Yeah? And I mean, that was a pretty simple insight in many ways. Yeah, I mean, said, okay, let's just make the superconductor, this overall metallic structure larger. And we said, okay, let's just do it. And then everybody did it and worked out fantastically. And at that point, basically, I decided this could really work out. So, I mean, the qubits had made a jump to a level where the overall goal of building quantum computers seemed realistic. And decided to think about how to, what would be applications for quantum computers. And for this, we also wanted to use, let's say, our background, I wanted to use my background in coherence theory. So really think about, you have a quantum computer, there's still this, noise and this fact that your quantum computers, your qubits are noisy, but you want to still find applications for these noisy quantum computers. And also in 2012, 3 master and then PhD students started to work with me in academia. And with them together, we would then create the company in 2017. And maybe after this breakthrough in 2012, there were, let's say, progress made on a steady level. And the really big additional thing was this idea of IBM to put just a chip of 5 qubits into the cloud. I mean, this was also, of course, really nice as a first step where people could just see that here it is. You can, send a signal or some small program to this device that really is there in the cloud and get something back. I mean, it was very noisy still, yeah. But that was really also a really big step to get a lot of interest from people who wanted to use these quantum computers. And then we started to do consulting for BASF and Bosch. These are two big companies, BASF, a chemistry company, and Bosch in, I mean, they do all types of stuff, but they do also a lot of material science. On the goal of using quantum computers in material science, which is also our key, let's say, is the key topic um, of our company, but more generally, the goal of what we do is to generally solve problems on a quantum mechanical level. That can, of course, be problems that are intrinsically quantum mechanical. Maybe a couple of words later on that. But also, if you want to calculate material properties, you often want to do this by solving the laws of quantum mechanics, because in principle we can describe anything simply by solving the laws of quantum mechanics, and we don't do it because it's very difficult for a conventional computer. You can do it to some extent, but it's very difficult. And so you would also want to use quantum computers in the future to do that faster or more precise.
Would it be fair to say that during the time since 2007, the superconducting versions of quantum computers have been the ones that are pushing the boundaries in terms of what you can do in terms of applications and sort of computational power? Because we can get into this perhaps further in the talk, but there are different kinds of quantum computers, right? So you have the photonic ones, yes. Superconducting ones is another kind. And based on your introduction here, it sounds like since 2007, when the superconducting versions came on the scene, they've sort of been pushing the bound. Is that a fair assessment?
I would say yes. Of course, I come from the field, I mean, quite a few qubit topics have made progress. I would say, especially in terms of this progress in regards to improving the quality of the individual qubit. I think it is really fair to say that superconducting qubits have made the largest jump and the most reproducible jump. So where, the improvement in quality do not require an insanely huge level of fabrication improvement, but it was just really gain in understanding and in understanding of the design. So the most easy to reproduce type of improvements, which then of course makes it very attractive for lots of people to try to really build a quantum computer from this type of architecture. So I would say yes, superconducting qubits have probably been the ones that have been pushing the boundaries a lot. Yeah, and I cannot think of quite another architecture. I mean, if you think about the architectures, there are probably, let's say, the ones that are actually available currently are mostly two. Superconducting and so-called trapped atoms or trapped ions, which is a single atom or a single charged atom, which you trap in an electromagnetic, in some form electromagnetic trap, which you can form through an electromagnetic field or through laser, for example. And these are the two architectures that are most common. And I would say, this type of trapped atom architectures have already been relatively good 10 years ago, which also means they're still pretty good today, but they have not in that way made that type of progress or jumps as superconducting qubits.
Mm-hmm. And if we talk about the industry as a whole of quantum computers, that is, there is this topic of quantum supremacy, which is, to my understanding, when quantum computers generally outperform classical computers on various applications. Are there any particular fields where we've reached that yet, would you say? And for the vast number of fields, I would say that we haven't reached that yet. What is the main problem right now that's preventing us from doing so? Is it scaling up, just our ability to scale the number of qubits in quantum computers, or would you say it's something else?
Okay, let's get started with where quantum supremacy or quantum advantage has been achieved. I use these terms normally interchangeably. And I mean, okay, there are some, okay, let's maybe define this a little bit. So quantum supremacy normally means that you do something on a quantum computer that cannot be repeated or only with huge difficulty repeated using conventional computers. Yeah? So you would need basically a supercomputing center and need to run the whole supercomputing center for weeks or maybe even years to do the same thing you did on a quantum computer. Now, of course, you can weaken this a little and say you need like a really pretty big workstation and computers and run it for a month to repeat this on the quantum computer. But I mean, this is like the scale. And there has been one experiment that also has been done now several times. There is a set of problems called sampling problems where quantum advantage or quantum supremacy has been achieved. Of course, this is again contested depending on how you define it, because then people achieved it, then other people improved algorithms, did the sampling problems also pretty big pretty fast using GPU clusters. But I would still say the sampling problems are in a range where one can say quantum supremacy has been achieved. Now I keep it vague when I say the sampling problems, because even to explain exactly what is being sampled here is a bit difficult. So these are very abstract mathematical problems where you take random numbers from some type of probability distribution, which is basically not uncreatable so easily on a classical computer. Yeah? And it's not completely clear where this would be useful for any type of application. There are interesting ideas to make this useful in generative AI, where taking numbers as a first step in your generative AI, random numbers from some type of probability distribution can be important. I think that's a super interesting direction. I have not seen that really this has led to applications yet, but I think it's a very interesting direction people are looking into. And it's one of the closest one to using really something that has achieved quantum supremacy to generate actual application. So now, what are the other topics where you want to generate quantum supremacy? I would say the big topic that many people look into is this type of topic where you use the quantum computer to simulate something that is quantum mechanical. And actually, once you have that, there is again actually a somewhat closer connection again to machine learning. But maybe let's keep this for later. So generally, it's relatively clear. If you have a quantum computer, you should be able to solve an intrinsically quantum mechanical problem using this device. And I would say the limiting factor remains the quality of the individual qubits.
Okay.
To really do that. Yeah. You have a certain amount of time that you can run your quantum computer. And if you initialize your qubits in a certain state and then start, running an algorithm. For the first few steps of your algorithm, you can still find very efficient ways to simulate it on a classical computer. In some sense, you can imagine it just in a really trivial way. If you initialize your quantum mechanical bits in like classical bits, you put them at 0 or 1, for example. And if I do nothing on these qubits, then of course that's very trivial to put in the memory of a classical computer. Yeah. And the first few steps in your algorithms do not that much more than keep your initial state. They make your initial state a little bit more complicated, but it's still very easy to keep track of that. And only then you basically build up what's called entanglement. And then you start to really need a larger and larger vector you put in your memory to really keep track of everything that also happens in the quantum computer. And so you need to run your algorithms for longer times than you currently can, because your errors accumulate in a way that currently just limits things you can do. And I think this is the major limiting factor. And so the quality of the individual qubits need to improve a little bit more beyond the level where we currently are.
Mm-hmm.
I can actually specify this a little bit more if just for
Sure.
interest. So I mean, currently you for example would specify you can specify it roughly by saying there is a certain error probability. So for example, if I tell you there's a 1% error probability, then this would say something you can do like 100 operations before one error occurs. That is not exactly what really is happening with this error probability in the actual device, but it's good enough to imagine it like this. And I would say currently really good devices have an error probability of maybe 0.5%, but that's really good and very limited amount of devices available. And I would say you probably need to get to error probabilities of 0.25% or lower. So let's say half the existing error probabilities currently, um, to such that it becomes plausible for problems in this simulation space to achieve quantum advantage.
Okay. And if we use that as a segue perhaps to your company and the work that you're doing. So you're producing software for companies that are looking to model molecules and materials. And my understanding is you do that with classical software and to some extent also with quantum computers. Is that something? Okay,
Yes.
yes. And when would you go for a quantum computer based approach in that case? Like, are there specific circumstances where that is currently superior to using classical algorithms? Is it mainly a question then of computational complexity, or how come you would go for the quantum computer solution?
Yes, so right now we wouldn't go for, I mean, going for a quantum computer solution is, we sell software for quantum computing, yeah, but currently this is for research purposes, where also people are interested in running these problems on quantum computers to see how the quantum computer performs, to see what you can do to improve various stages of your readout, maybe do additional tricks to reduce this error levels and so on. In kind of the industry level software, currently still everything runs on a conventional computer. But there are various steps that you would like in the future to kind of put to the quantum computer, and um, in some sense, it depends on something that's not so easy to quantify, and that's why it's also good to first run everything on a conventional computer. I would say it also depends on the quantum mechanicness of the
Mhm.
problem. Yeah. If you solve problems that are microscopic, for example, you have um, a small transistor and have various materials in your small transistor, and you want to calculate the conductivity depending on the disorder in the silicon or on doping levels. So how many additional doping atoms you bring into it, and so on and so on. These are kind of interesting problems that you also can kind of predict, and where lots of people do, I mean, a huge amount of work, since you, of course, want to miniaturize all types
Mhm.
of things. And there you kind of can do full quantum mechanical calculations, but there are also, to some extent, approximations available that allow you to calculate this type of properties like electron conductivity uh, using various modeling stages. And this modeling goes kind of goes through all types of sizes of your problem. It's often called multi-scale modeling, and that is also why we have a classical or a kind of a software stack for conventional computers. Also, that in the future you can't go through all these different size scales, and then only as you are on a small level of problems, you really use the quantum computer, extract a certain amount of parameters for that, and that you put into a larger scale of your
Mhm.
problem. Yeah. Um, and then, for example, you can also use your quantum computer in the future to calculate certain parameters that you do like once. So you calculate it once, in a maybe quite expensive way, like quantum computer, but then you have it in a toolbox and can reuse it again and again and again for more large scale simulation using kind of a more approximate method that just takes a parameterized model. as an input.
And that kind of brings us to some of the offerings I think that you have from a commercial point of view on your website. So on your website, there are three main products listed. So there's bespoke simulation software. You then have the HQS Quantum Assisted Design Cloud. And then lastly, you have open source software. And I think when it comes to the open source software, this is something I think we can get into if we have time. You collaborated with Planck to create some form of application space where you can reuse parts of the products that have been developed. So I would assume then that for these kinds of quantum snippets, let's say, of code that you would develop for a specific application, that the vision would be that they could go into a space like that and that you could reuse them also in the wider community. But to not get ahead of ourselves, maybe we can talk briefly about the main offerings that you have on your page. So the three ones that I just mentioned, you can start with whichever one you think makes the most sense.
Yeah, I mean, the bespoke software development is especially in this area of multi-scale simulation, because often these problems are can be problem specific. So you have a very specific problems, and then you need to go through various size stages. So it's very important for you, and also then important for you, for the customer, in terms of having a competitive edge that is exclusive to you. Yeah? That's why we do this kind of bespoke then for a customer as the exclusive software project, where the more generic part that also comes then specific from us, which we have several times, is only the part where you would put in the future a quantum computer. So where it gets really quantum mechanical. We say, okay, I mean, there's a lot of stuff going on, from relatively large scale problems to kind of smaller and smaller and smaller. And then as we go to small problems, there are specific tools that can be put in that we also then reuse to some extent. It can also be open source, but where the quantum mechanics also on a relatively abstract level can be solved. So this is like the bespoke part of what we do, which helps the customer to have actually direct gains today, and also helps us a little bit to direct a little bit, have a better view of where the quantum computer really needs to go if we want to plug it in this quantum subset of problems in the future. Now, the cloud is in some sense an attempt to make all these offerings more generally available. I would say currently the cloud is in a better stage. Yeah? There is quite a bit of quantum computing parts in it, various kind of parts on quantum chemistry, which is, say, calculating molecular properties. And in the future, there will be more parts that will be related to calculating spectral properties. Just to explain what this means, is if you have, for example, some liquid and you know there are molecules in it, you would, for example, irradiate this liquid with microwaves and then see what you put some microwaves in and get some microwaves out, and you want to know what kind of microwave frequencies have you gotten out. And this tells you something about the molecules you have in your liquid. And that is a very nice problem in many ways. It's quite important in many areas of chemistry and pharmaceuticals. And it's also a problem where the quantum mechanics can come quite strongly. So that is like one thing we're going to add, and we're going to add a couple of tools related to calculating electronic properties, so electronic conductivity properties of materials. This is the cloud. And now the open source tools we have. This is the snippets part that you mentioned. We have a set of open source tools that is very strongly related to how we believe the quantum computer will be addressed in the future. So many people currently, when they build, for example, also cloud offerings, or when they offer their own quantum computers, they give people API access, meaning you have in your Python code, you can call, it's mostly Python based, you can call some function that then goes into the internet, calls the quantum computer, and then sends a snippet of code to this quantum computer. And Our impression was that as somebody who offers quantum computing software now and in the future, it is best for us to create intermediate levels where, for example, if we create something that you want to run on a quantum computer, we create an output, what we call a quantum program. That is a very small piece of code. So we have like a huge stack that, for example, does this pre-calculation for molecules, like classical calculation, all types of stuff. And then in the end, we create something for you that you want to run on a quantum computer. And this is just packaged in a small amount of code called quantum program, which you can also, then kind of store as a JSON file, also a very standard serialized format for use in various cloud platforms. And then you yourself can send it wherever you want to send it. And basically, we have then open source backends. So if you are a user of a specific actually quantum computing platform, you can send it to any kind of quantum computing platform using your own tokens or your own access in whatever way is convenient for you. You can write your own backends as well. You can translate it, and we have already also translation software of our program into other formats and so on and so on. So there's one very slim format that basically everything goes in and kind of gets kind of transformed into one another, and such that, for example, what this does is it kind of avoids that suddenly you have breaking changes in the backend and some stuff doesn't work anymore. The quantum program stays the same, and you just have to fix this one backend for your quantum program, and it's all going to be always open source.
Mhm. So,
So this is like a key. Yes.
sorry, one question on the serialization into JSON format of this.
Mhm.
So, whenever you have APIs, at least as far as I'm familiar, you would send, you would have a very specific application for what would be calculated. You would send, for example, some data model of the actual thing that you want to feed this calculation, and you would get a return in the same format that you could then deserialize. In the applications that you were talking about, is it the same principle, or are you also saying that functionality itself would be encoded within that serialized object? Because the reason why I'm asking is I'm thinking whenever you have these code snippets that you want to send, like a quantum program, I guess there would be a lot of flexibility in terms of how you want to define that and the types of calculations that you would like to perform. And if you wanted to define APIs for all of those kinds of calculations, you would have a very large task ahead of you to create all of those, APIs. Can you maybe elaborate a bit more on that?
Yes. This is exactly what you say is a huge issue in the community right now, I would say. Because you would, in fact, like to encode functionalities in your quantum program and send it through an API. Instead, what's currently happening is you do not encode it in your quantum program and send it to the end device, but you call the API again and again and again, which creates a terrible kind of problem in your traffic, because you need to send something, get it back, do some kind of really minor calculation or minor change on your end and send it again. And many people work on this and sometimes called runtime frameworks and so on and so on, so that there are various ways to solve it. One very simple way to solve it, and which also is, let's say, one way we recommend and how our kind of own quantum program format is thought of, is, you provide a workstation that your customer can log in, with just some kind of standard SSH or whatever, I don't know, some super simple way of uploading something. So minor kind of way of sending some info, really copying some complete information. So, and then this workstation stands directly next to your device. So there is no cloud anymore. It's directly the thing that can access your device directly. And then, because you as the customer do not necessarily want to upload all your complete software stack to that, but then you can just upload the quantum program and maybe some minimal extra functionality that would kind of do something. And then you just again call the API, but then you do it again and again and again. And it doesn't matter that you do not have it fully serialized. You do it basically just because it's now, you do not have the whole latency of the cloud anymore. Yeah? And you can't keep, in some sense, then the API is not in that sense an API. It's just the way to get really from, because I mean, you always have a classical computer that controls the quantum computer, and it's just this one last connection, yeah, of literally, maybe I don't know exactly how it's really in the lab, but of almost literally a classical computer, maybe a laptop even, standing right next to the quantum computer. So this is the way to go. Now, to make this whole serialization easier, we indeed have certain constraints on and certain thoughts of what problems you will also set. So the way it's built up, it of course has a certain focus on this type of simulation problem, where you do have this kind of thing that, for example, you have a code snippet that you run that is in some sense an algorithm, and you run this piece of operations on your device once and collect results. Then you run it twice and collect results. Then you run it 3 times and collect results. Yeah? And this is extremely easy because I send you once this instruction set and tell you run it once, show me the results. Then run it twice, show me the results. Run it 3 times, show me the results. Yeah? And so it's a very easy set which you do not want to just call an API again and again just for such a simple set of instructions. You want to kind of put this in one JSON file, send it, and then do it at the end of the kind of the provider. Yeah?
Okay. And on the different modules that you create in partly the bespoke software applications that you build, but then I'm assuming also on the cloud, whenever you're modeling on really the quantum level now, the different molecules or whatever it might be, do you model all aspects of that? I'm thinking specifically how rich the data model for the individual, let's say, particles or even subatomic particles. I don't know how small the different quantities you model is. How much simplification can you do there? And as a follow-up question to that, does it alter your approach a lot in the smallest computational modules, depending on what application the client is asking for? How generalizable is the software?
I mean, there are very general problems that, I mean, actually appear to some extent general, but they appear in a similar way in many problems that you have. Like, you have a big matrix and you need to diagonalize it, or you need to sample it, or whatever. Yeah, I mean, these are problems that are well known in many areas, and similar problems then appear as you really go down to the very abstract level of things you do. But let me maybe first address this data richness issue. A general fact about quantum mechanics is that, while solving quantum mechanical problems, is that the amount of input you have is very small. And the problem is very difficult. This also as maybe fact of interest. If you think about what problems run fast on a quantum computer, these are always problems that sometimes are expressed as, small in input, heavy in compute. So very little input data, but very difficult problem to then solve based on that, based on this little input. So in some sense, if you specify a molecule, you can specify it by saying I have 80 atoms, and then you tell me what type of atoms that are. Okay, and that's it. And from this onward, there are only instructions that build up the whole problem. Yeah. So there's, in some sense, the input is extremely small. Now, of course, in practice, this can become arbitrarily complicated. Yeah, but I mean, this is fundamental to the type of problem that, in principle, at first at least, the problem is very simple or very small in the amount of input data, and then, of course, every stage becomes more. Now, how generalizable is the things that we do then as we break it down to the quantum level? Actually, that is extremely difficult to say in a general way. In principle, you always want to make it as general as possible, but I don't know. I mean, my feeling is that everybody who has worked on any computational difficult problem always notices that you use a functionality that in principle should be very general, and then you do it, and it turns out it's not actually that general, and you can improve it a lot given specific knowledge about your problem. I'm not sure how this is for your case in your day-to-day work, but I think this is a very general issue that appears very often, that it turns out that problems can be improved, or solving a problem can be improved a lot once you put in more knowledge and more know-how about the problem itself.
Mhm. Where I'm coming
But in
from,
principle, you can. Yeah, sorry.
where I'm coming
Yes.
from specifically with my question is maybe a
Yes.
parallel to game development. So when you do game development, for example, you would have some physics engine that is running in the background that has some internal data model of, let's say, how the universe functions, and that particular piece of code is generalizable across all the different circumstances that you would find your character in or whatever. My question is not so much on the data model that you provide to the calculation, but more of the internal representation whenever you do these quantum mechanical calculations. I'm thinking particularly when it comes to material investigations. So let's say you're trying to model some atom internally, or the well, components that make up your particular atom on whichever level it might be. Do you, for example, have a very rich model where you model, for example, the fields that are surrounding this atom always? Or are you able to make simplifications on that data model depending on the application? So, Mike, yeah, please go ahead.
And in principle, you have a very compact model that is universal. So you actually start from an absolutely universal model that is extremely simple to write down. Then, once you get down to how you actually solve it, all the problems arise. I think this is what also makes it a bit different from the way you would model it in a game, where probably you rather put in more data but have the time to evaluate the model piece fast. In principle, if you solve problems quantum mechanically, the central aspect of it is that writing fundamentally down the model of the world is in some sense extremely simple. But then actually evaluating something that comes out of this. Yeah, for example, light refraction, something you would also evaluate maybe in a game. Yeah, you have certain materials that reflect light in a way. I'm not sure if this is really put in the physics engine, but I don't know. Yeah. Uh, and evaluating this can be, even if the model that you write down and all the fields and the electromagnetic field that represents the light and so on, writing this down on a piece of paper can be extremely quick. Yeah? But then solving it and seeing kind of how is light now refracted after all can be extremely challenging.
Mhm. Okay, yes. If we bring this now to some of the research involvements that you've collaborated with, so different universities, different institutions, I think the first one we could talk about is the one we mentioned before, namely Planck, and the involvement you had there. I believe this research initiative is now concluded. If you could maybe speak briefly about that initiative as a whole, what you were trying to do, like the ambition, and also if there were any concrete takeaways that you got from, well, any concrete products that were delivered as a consequence.
Um, I'm not sure if the Planck platform itself has been open to the public completely yet, but it exists and is finished and it's been used by all types of, let's say, beta users. And so, yeah, so Planck was a project to create a kind of platform that would allow you to, for example, very easily access applications and connect them to a backend and so on. And I think from looking into this question of how this would work, we developed our own intermediate representation um, to kind of simplify this question, because direct API access of a platform to a hardware device is, in our view, will stay a little bit challenging. Um, and I think the platform currently serves mostly as a kind of a platform for collaboration and as knowledge base for algorithms and so on, and will in the future then connect, kind of use really built in more applications. So currently this is managed by a company from Berlin called Encore, and they manage and continue to manage this platform
Mhm.
and its outcome. Um, so this was the Planck project. And again, for us, the major outcome was the intermediate representation which we created, which is open source, um, which gives us a more easy to use accessibility, kind of from devices and compatibility.
Mhm. In terms of your work, how much open source software from other parties do you actually leverage? And is your experience that there is a big need for a consolidated platform that allows people to share the software they write in a more seamless way?
So we are using a lot of open source software in the space of material science simulation. I mean, very often, especially when we do a bespoke software project, we first start to evaluate existing tools in a particular space, and then we start to actually build the software. On the quantum computing side, we also use some open source tools, but we also write more our own software. Do I feel that there is a need for a sharing tool of software? I mean, do you mean something like GitHub for quantum mechanics?
Maybe like GitHub or something that I'm not convinced that GitHub necessarily has the right structure for something very industry specific. Like, let's say you're coming at this from
Mm-hmm.
the quantum application space. Maybe you want a
Mm-hmm.
different way of locating the software as opposed to GitHub, where it's more like a, at least the way I've used GitHub in the past, you have a link to a repository from that you usually find somewhere else, and then you find the repository by means of the link. I'm thinking more maybe
Mm-hmm.
some platform where the objective of the platform is to locate software for you and help you do that.
I mean, yes. So, I mean, it's an interesting point, and you correctly brought up Planck in that context, since, of course, the combination also of algorithmic information that is fundamental to the algorithm, general knowledge about what can actually be done in that and how quantum computers work, and then the code snippet, or combining these things is quite important, I think, currently in this space. Since, I mean, it's fundamentally explaining to people what actually a piece of code does is a very important part of actually enabling you to use it. And I think the Blank platform does that already. And I think that is a good attempt to restructure these ideas about how to share, let's say, let's not just say code, to share information um, uh, for quantum computing related information. So, in some sense, it is probably true for us. Specifically, one thing we look at is similarly how to better. I mean, a really important part in all quantum mechanical calculation is, for example, modeling. You do some calculation and then you take some parameters out of it and put it in a more abstract model. And going to this modeling level can be very valuable, but it's also very difficult to share information about how to build this model and for what it was built and how you can generalize this. Because often it's not immediately obvious. Yeah, I mean, you did it for yourself and it's very useful for you because you understood it. And you are probably also very, I mean, people who build this model are then normally very skilled in very industry specific
Mm.
topics. So they know normally the software well, they know the molecule or whatever, or the semiconductor they work on very well. So they're very experienced people that then do some modeling effort and then also have a mathematical model that they also solve using some software, some quantum mechanical model even. And I mean, in our field, this question of how to improve sharing models and how to make this more generalizable is an important one on which our own platform also, let's say, we're working on this to some extent. And the way we currently go about it is that we create, in some sense, what we call input schemas, where you limit the amount of information you can give to your code, but in a way you specify it also again serializable format, and what in the end can be a JSON file, but also can be directly transported into a graphical user interface, such that you have certain parameters that are named, and then you can also directly give information on why. So you can directly put in some sense, links to a knowledge base, or directly put in information and tell users why that is the relevant information, how it connects to other problems. So this is the way we try to go about it. Sounds probably pretty abstract because the problems are pretty abstract and also do in fact require still a lot of knowledge about quantum mechanics. But yeah, I mean, this is actually a really interesting point that does come up quite often. How for industry specific topics you share information that in the end is always connected to code, but not is not only about the code. It's about also why would you use it, how would you connect it to something else, yeah, and so on. Yeah, so this is indeed a very interesting topic.
I want to look forward a little bit as well. So, partly on the kinds of aspirations you have with the company, and then also where you see the industry going. One initiative that I saw you were also involved in is what's called Faux Quant, which is the development of a photonic quantum computer. Can you explain where in the grand scheme of things you fit into the picture there? Is it mainly on the software side of the things you develop, and how generalizable that is across quantum computers? Because the reason why I'm asking is, given the background that we discussed in superconducting quantum computers, is most of that transferable to another kind of quantum computer like a photonic one?
So, I mean, first to answer it's generalizable, let's answer this is yes. There are specific, very interesting topics. I sometimes like to talk about that. Let's say where the type of quantum computer I use become more important in its details. But I mean, in general, of course, we try to keep it as general and generalizable as possible. Especially, for example, these intermediate layers and so on and so on. All this is should be and is currently very generalizable, especially when it comes to the background hardware. Now, actually, Focon is an excellent example for the things we do and want to do in the future. Because, I mean, in Focon, we actually do two things. One is we work on quantum mechanical calculation for the materials and for the devices themselves using conventional computers. And, on using quantum computers in the future to also do this type of material calculation, the material science calculations, and also device calculations if necessary. I don't know. I mean, of course, we are, I think, still a little bit away from using a quantum computer to simulate a quantum computer, but sooner or later it's going to happen. So both these things together. I mean, in general, our goal is to solve all quantum mechanical issues that any customer might have, even if the customer doesn't even know that it's quantum mechanical. I mean, it doesn't have to interest them. Yeah, and probably they should know that it's microscopic in origin. That like small scale atomic scales are involved in some way. But then, of course, all the things what happens under the hood is our business. Of course, that's not quite where we are. Currently, users have to bring their own knowledge, and we also then work in more detail with customers on there may be researchy questions for them. Will it work on a quantum in the future? And what gains will this produce? How do we solve it right now? And what are the optimal methods? And how do we make it work? But these are two things in Foquant which we do. And then, of course, we want to be the one-stop shop. Is that what something people say? But anyway, yeah, for all problems in the microscopic scale.
Mm-hmm. Okay, that's very good. So, also looking forward with the kinds of products that you're looking to take on in the future. Are you looking for something in particular, maybe in the upcoming year, that you're trying to specifically cater towards, or is it sticking to the strategy that I think you've kept for quite some time?
The actually specific topics we like quite a bit and look also into is, I don't know, I mean, the question if more devices that you want to build in the future will use quantum mechanics as an intrinsic part of their functionality. And not just, I mean, of course, somehow you and me, we function because of quantum mechanics, because everything is based on quantum mechanics in some sense. But this is not exactly true, since I could make a model of all things happening in the human that needs no quantum
Mhm.
mechanics. Only parameters that go into that would need to be explained by quantum mechanics. But I mean, you can think about devices, and this is especially an interesting topic in all types things related to sensors, or in all types of things related maybe also to light emission, even in like screens of your mobile phone and similar things like this, that use on a more intrinsic level quantum mechanics. And this is a very interesting topic, which also could grow, I guess, and where we look quite into it, because of course, I mean, quantum mechanics simulation are best if even the functional principles of what you want to do are based on quantum
Mhm.
mechanics. So it's a very interesting topics, um, where we will see how this progress, kind of what the progress of this is. So, for example, in the medical space, that various medical imaging techniques could in the future rely on fundamentally using quantum mechanical parts of the sensor is quite
Mhm.
probable. I mean, I would say it's not guaranteed, but it's pretty probable. And that would, of course, be a huge space of new devices, new developments, um, where also the needs to kind of improve your devices through numerical modeling would probably explode.
Mhm. Okay, that's very interesting. So, in terms of my selfish interests, looking forward, are there any initiatives that you see in the space that you think have been very interesting and that you would recommend that I try to get in touch with? Like any developments in the quantum, either quantum computer space or the quantum simulation space that you've seen recently that you think are very, very interesting from your point of view?
I mean, you already mentioned Planck and the company behind it. If you Google Planck and Anchor, you will find them. I think they are from the software development perspective. Have certainly also probably interesting things to add. Um, Otherwise, of course, there are these really big um, quantum computing initiatives that are currently going on. And from that, I mean, I might recommend an initiative called QXA, like Q, of course, like in quantum, and Exa, like in exascale computing.
Mm-hmm.
It's an initiative. I think it's led by. It's led by the hardware company called IQM. But for example, somebody to talk to is also the High Performance Computing Center in München, Leibniz Rechenzentrum,
Mm-hmm.
and their initiatives in quantum computing. I mean, that might also be a good combination of quantum computing on one side, but also the more, let's say, numerics and computing heavy topics.
Perfect. And Michael, for people that want to get in contact with you, either in terms of potential business collaborations or just for general questions, where would you recommend they try to reach out?
They can use I mean, if they check out our webpage and the contact part of it, there's an email address called info at quantumsimulations.de.
Mm-hmm.
So quantumsimulations.de is our web address, and then just info at web address. Yeah, I mean, very clear, like many people. And I mean, we read this type of emails, they do not disappear. So if you want to reach out to us, this is the best way.
Perfect. Then, Michael, I would just thank you very much for taking the time to speak to me today, and it's been a pleasure having you on board.
Yeah, thanks. It was nice to talk to you too.